Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He's probably most known American expert in embedded systems, and deservingly so. As an acting director at DARPA, he started major initiatives in embedded systems. And his research straddles many areas, in particular control theory. In particular, it's an interesting place where control theory and software engineering and system theory intersect fruitfully. Probably what is less known, that he started his career winning some mathematical Olympiads in country where where it is notoriously hard to do. Hungary. Okay, welcome, Janusz.
Thank you. I was just participating in these things, and but I love mathematics, and I was in the same age group as Laci was, and he brutally beat me up in all of the conceivable competitions where I participated. Well, anyhow, thank you very much for the introduction. It's a pleasure to come here, and indeed, as Yuri told, I'm working in an area which is somewhere in the intersection of several fields, and that leads to the topic what I would like to talk about, which is modeling languages and semantics of domain-specific modeling languages. There are many names for it: model-driven engineering, model-driven design, model-driven architecture. Model somewhere is in all of these descriptions and titles. I will talk about four things. One is the application context. Obviously, that determines a whole lot how I view things. The other one is a tool suite, because all of the work what we are doing is translated into a tool suite, which is distributed and used many places. And finally, I get to this topic, what I'm interested lately quite a bit, related to semantics of modeling languages, and some words about what's the road ahead, how I see it. Let me tell about these application drivers. There are three areas. Of course, I could define four or more, but let's say three areas where there is a quite fascinating convergence is going on. And this is software control and systems engineering. The application categories what we deal with quite a bit relate to large-scale embedded systems. Don't think about watches and PDAs. But bigger things: airplanes, target recognition systems, many these kind of military application styles. But frankly, this whole thing relates to a changed role of information technology in the modern world. Before, computing was primarily used to implement algorithms, certain kind of algorithms, and compute things out. Computing these days is primarily used for system integration. Computing and communication is the media which glues together very large systems. And that new role of computing really changes a whole lot, I believe, all of these industries, including software. Interestingly, this topic is much hotter in the control and systems companies. Perhaps necessarily than in your company, simply because these are the companies that are turned upside down because of these changes. Now, that fusion of these three areas means that whenever these days you design control systems, most of the control algorithms, control methods are implemented algorithmically using software methods. That enables totally new kind of control laws. And there is obviously a pretty intimate interaction between the software and the control part. For example, robust control, which is prepared for developing control systems that can survive all sorts of failures, has to handle now software failures, software design failures, and generally in critical systems such as flight controller, new interface has to emerge which fuses software and control such that that in the software construction side, you take into consideration basic principles such as system passivity that provides tremendous robustness against classical software issues such as quantization errors, round-off errors, and even different kind of uncertainties, communication uncertainties. The systems industry, of course, is the industry which is the Boeings, the Raytheons, and these companies who are gluing together these large systems. The primary concern is fault tolerance, reliability, survivability of these large systems, how to manage the complexity of these large systems. Systems engineering is their livelihood. So really what's happening now that due to this overall interaction, convergence, people started looking into how to develop different design technologies, implementation technologies that can link more intimately together these different areas. And of course, what's emerging is a modeling layer. Modeling is a very known quantity for control engineers and systems engineers. That's how they are trained. So interestingly, modeling is a much newer concept in software engineering. But certainly the last 10, 15 years brought up a lot of these kind of directions led by modeling languages and directions like UML and others. Modeling really, the decorative style modeling really seems to provide an overall approach with which we can link together all of these disciplines and develop design methodologies that are very tightly coupled together. What we gained with the introduction of this cross-cutting modeling layer are first abstractions, appropriate abstractions that can manage heterogeneity, that have integrative concepts across these fields that are safe and sound. These abstractions evolve for a longer time, so it's very important to understand what are the good abstractions and the not so good abstractions in the area. Other major concern in this new area of system design is integration. As you might know that right now for large military systems, the system integration cost eats up half of the budget, roughly, between 40 and 60% of the overall development cost. And that's because there is no good compositional theory for building large-scale systems where the composition means that with the usual engineering tools, when you take the properties of components, you can calculate what will be the property of the compose system. Therefore, much of the integration technology these days is experimental. You build the components, take it into the system integration lab, and you start to test it. And of course, because these systems are very complicated, you can never test them, basically. You test these systems until the money runs out. And the results are those things what you use occasionally in the newspapers, that one of the very large program which built a certain airplane achieved that after putting together the integrated software for the airplane, the software was stable for about 8 minutes. The whole fleet was grounded and the program was grounded, and it cost about $1 million per day for DoD. So these kind of things are really the major concerns in this whole intersection area. So obviously here from the integration point of view, the the overall driver is to make it affordable, model-based, end-to-end, and manage much better heterogeneity. And finally, automation is a big thing. So if modeling is available, everyone is seeking for building up a modeling infrastructure which is formal and manipulable, which means that it's solid enough that you can develop design automation tools for the overall systems software engineering. And that's another issue, and I will talk about this later. Now, some of the areas where we've been working on, we've built signal processing toolchain for Raytheon for really a large category of applications. It might be funny, I'm a professor at a university, but my institute is about 100 people, and we have about 35 professional research staff. So when I'm talking about we are building systems, that's because not we have to work the same way as these professional research organizations working who have to produce things to survive. So one area where we work on is signal processing toolchain for Raytheon. The signal processing toolchain are typically providing embedded computing for many areas: automated target recognition, signal classification, communication. They are highly resource-constrained underlying hardware platforms that have to be modeled, resource-constrained, have to be explicitly part of the overall design process. Systems need to be generated on a variety of underlying computing devices, from FPGAs to RISC processors. Dynamic reconfiguration is occasionally an issue, and they very heavily push the product family support. You will see that theme again and again, that the style how we build up these tool chains, that we specify a suite of different modeling languages that capture important aspects of the problems. We do component modeling, software architecture modeling, design space modeling, and others. We use that these models for analysis, and then use the models for generating different kind of artifacts what you need for the underlying system. Our biggest project right now is our participation in the so-called Future Combat System program. Boeing and SAIC are the lead system integrators. That's altogether it's a $28 billion software program. That's rebuilding the Army for lightweight vehicles, highly network-based. And you can imagine that that's a major change in the industry, how to build these systems. What we started doing with the Boeing team is using modeling for architecture exploration and system integration. One interesting aspect of this project has been that the different system components have to be designed by the architect team. Then the architect team has to send it out, the architecture specification, to subcontractors, to many other companies. They are participants from all 50 states, needless to say. Then the designed components are coming back, and Boeing needs to integrate it. So the technology clearly is not ready for that. It's very interesting to see what kind of properties the architectures can guarantee before you build actually the artifacts themselves. And that's why this architecture exploration is becoming a very important and very challenging issue. This is a capture of the tool environment. What I just want to flesh out again, what are the core elements here. We have a modeling environment, what we use for defining modeling languages and building models. We have a model transformation technology, which in this overall flow takes the different kind of architecture models and translate them toward different tools. Translate them, for example, toward discrete simulators to test timing properties, such that you define the basic component behaviors as basic time automata. Generates from the architecture model fault trees and sends it to a tool which does preliminary fault analysis. A quite rich variety of information processing going on, basically systems modeling and transformation of the models. Lately, we started up a project with them which is a incremental system integration project. What Boeing is doing with these tools, that they are building up the different architecture models. From the architecture models, they create so-called surrogate components, synthesize the whole system basically from components that are not ready yet. But their behaviors is captured at a higher level of abstraction. And they incrementally want to replace these components with the final components. So the whole intention is that they always have some kind of version of the system. And there won't be a one-shot system integration at the end of it. There are many other applications. We work with General Motors on a vehicle control platform. That will come up later. I will show that semantic encoding of that language, what they come up with an avionics platform with Boeing, a large manufacturing execution systems. We worked quite a bit on the space station diagnosability modeling and analysis. So basically the underlying theme what you see coming up here. These are typically large systems where computing or computational objects and physical objects are all combined together to perform functions. And whenever that happens, you need to take an overall systems view and work out different representations that make possible that you can integrate and test properties of these widely different kind of things. Now, let me go to where all of that work led us and what we call now model integrated computing and model integrated computing tool suite. What are the elements of it? Finally, we ended up with a layered architecture. That layered architecture includes, on the top, different domain-specific modeling, model analysis, and model transformation environments. These are the things that are the automotive tool chain, the avionics tool chain, signal processing tool chain, and others. They all have their own unique interwoven languages and their own concerns, analysis methods. Obviously, the primary challenge here is that if you want to build domain-specific environments, on one hand, domain specificity gains or provide the systems and software engineers a lot. They can really push the abstraction toward where the problems are. They can select those aspects of the systems that are essential for the design. But in the same time, there is another pressure to build up design environments that are tailored to application domains is extremely expensive, and usually you cannot afford it. So if you look at a classical example for it, Simulink Stateflow, the MathWorks environment, I'm sure that many of you know that. Simulink Stateflow evolved during the last 20 years. It's an excellent environment. It's a highly domain-specific environment, and that's why it's so powerful. But it's very expensive to build up these things. So what really the challenge in this area is, how can you resolve that problem that you want to create this domain-specific environment, but you want to provide high level of reusability for an underlying infrastructure in them? And that leads to this whole second layer. This second layer, what we call the metaprogrammable tools and metaprogrammable environments layer, that includes a suite of tools, what I will talk briefly about it. These are generic model builders that are so-called metaprogrammable. I will explain what metaprogramming is. Model transformation tools, tool integration frameworks, data models, data management tools, design space exploration tools, all of them highly customizable. somehow it captures a highly reusable set of assets that you can turn into highly domain specific in many different kind of application domains. And finally, there is a semantic foundation layer. That's of course the interesting point, what we are these days heavily after. So let's just briefly talk about this middle layer. There are 5 elements here that we built up during the last many years. It supports modeling and metamodeling, model data management, transformation, tool integration, and design space exploration. The community who is dealing with these extended modeling languages pretty much adopted the following view for modeling languages. Domain-specific modeling language is defined through these concepts. It's defined by a concrete syntax which can be mapped into an abstract syntax through parsing. The abstract syntax captures the concepts, relationships, and well-formedness rules that you can express with a model. And then there is a semantic mapping which maps all of the semantically correct models or syntactically correct models onto a semantic domain which uses some kind of mathematical abstraction to define some sort of semantics. These can be behavioral or structural semantics depending on what kind of things you want from your modeling language to express. Now, whenever we want to define domain-specific modeling languages, obviously a key issue becoming, if you want to use design automation, that these specifications has to be precise. So obviously what comes up that you not only define the modeling language this way, but also use a particular formalism with which you can specify these modeling languages, the different element of these modeling languages, and these are the so-called metamodels. So metamodels are specifications of modeling languages, and the metamodeling languages are used for modeling languages. Here is an example, again, a quite common technique these days that are used for metamodeling, the abstract syntax of the modeling languages, using a language which is in that case it's shown is a graphical formalism. These are UML class diagrams. It's a type language, and the constraint language, which is OCL, the object constraint language. You could give another kind of concrete syntax for this. That doesn't matter. The thing is that for defining metamodels, you need to have a language which is rich enough to give you the opportunity to define concepts, relations, and constraints. And any kind of language which does it, it's good. We choose for our tool infrastructure version of UML class diagram and OCR simply because that started really spreading, and it was a good choice because it got standardized. So for example, what you see here is a metamodel of a modeling language which describes hierarchical state machines, and that thing here specifies all of the possible models what you can build, all of the possible hierarchical state machine models what you can build, which satisfies all of the constraints that has to be done. And here is a simple example for it. Now obviously an underlying tool, which is a modeling tool, which is customizable, has to be able to provide support for building the metamodels, because that's just another language, or has to be able to provide support also for building any kind of domain-specific models or domain models. So clearly that defines an agenda for building metaprogrammable tools for modeling. A metaprogrammable tool for modeling should have a core, a highly reusable core, and that highly reusable core can be metaprogrammed by reading in a metamodel which customizes its own behavior and turns basically the tool into a domain-specific modeling environment. That modeling tool is GME. We developed that on Microsoft platforms, and as all of our other tools, these are distributed, and there is a website, a quality control repository from which anyone can access to it. Another component in the overall tool suite is model management. When you build large models have to be stored somewhere. It has to be stored in many different kind of backends, in databases, in XML formats. Occasionally it has to be loaded in memory. All of these are different persistency format changes. Obviously, you don't want to develop for every one of the domain-specific modeling language a different kind of backend. But again, metaprogramming help. You can develop a tool suite which takes the specification of the domain-specific modeling language and compiles it down into different artifacts. For example, this tool suite is what you call UDM, Universal Data Model Tool Suite. That tool is doing a copy, and that copy means that you can translate the models out of GMER modeling to XML file format or binary file, or send it to the network. So different kind of backends translations are possible with this. Or also it can generate from the metamodels a binding, a language binding through which you can access from different languages to the underlying models that are created. This is again a non-trivial element of the metaprogrammable tools that have to be present in all of these technologies. The third major component of this is the model transformation. Model transformation is just penetrating through everywhere in this technology. This is very common. When you take a model, a domain-specific model, it's a very common requirement that you want to take out information from a model and package it up and send it to an analysis tool or a simulation tool, but using that language what that tool requires. Otherwise, you would need to customize again and again the tools to work very different kind of domain-specific tool chains. Now, obviously, if you want to do these transformations such that you take the concrete syntax and translate the concrete syntax to another concrete syntax of another DSML, that would be pretty hopeless and convoluted. Well, the solution what we pursued, and actually this is the generally applied solution these days, that you take the abstract syntax metamodel and define the transformation in terms of the abstract syntax metamodels of the source and the target languages. Obviously, that requires the definition of a transformation language and an underlying infrastructure, tool infrastructure which does it. That tool infrastructure, which was developed by my colleague Gabor Karsai at ISIS, uses a graph transformational semantics and the language which let you define the transformation is another domain-specific modeling language, which is modeled, of course, in the tools, in the modeling tools. And the underlying engine takes these transformation specifications and compiles it down to a transformation code. And that transformation code then can take the, through UDM, the models from any kind of backends and transform it and send it out another backend. So that's obviously a key component, and it's used everywhere in the technology. In fact, as you will see, we use that very heavily in this whole semantic anchoring approach. All of these elements let us to build up a tool integration framework which allows that through a tool adapters, tools can send back and forth data across each other such that if you need, you can perform a certain translation, conversion of the models, whatever the tools are requiring. So this is basically the overall tool infrastructure, the overall tool suite. Everything, all of these major components are circling around the metamodeling language and then different metamodels. They can be customized through the metamodel specifications, and that's how we build different environments. Here is just briefly running through an application, how we would build up things with that toolchain. That toolchain is a vehicle control platform, what we build up with General Motors Research Group. If you look it on the top, on the domain-specific language level, it has Simulink state flow. It has many other modeling sublanguages that were captured in our tool environment. It has a design space exploration tool. It has analysis tools, simulation tools, and basically there is a flow with which these tools can communicate and send data back and forth. We can do behavioral modeling in Simulink state flow, component structure, component interaction modeling in our modeling environment. The schedulability analysis is done in another tool which was developed at Michigan. The Vector is a commercial product which does behavioral simulation. And you can see that combining these elements together, you get an overall design flow. The middle layer is much simpler. The middle layer, which unifies a lot of things. So there are much domain specificity there in terms of many different kinds of notation, graphics, and accidental complexities. What you see in the middle layer is the metamodels of the different domain-specific modeling languages and the specification of the transformation expressed in terms of metamodels and graph transformation rules. That really provides a very nice integration platform for gluing together these different tool chains. And finally, that design, that tool chain supports a design flow which starts with requirements specification, the controller design using Simulink state flow, then goes down to software architecture and software component design. There is an architecture specification which is done also with obviously modeling tools, a system architecture design, and finally a software deployment design. And that's the overall tool, the design flow, what comes out of this. There are many different kind of analysis components, analysis and verification components that are used at each stages. You can imagine what's going on here. And these are the outputs that are generated. Not only the functional code, but the OS firmware glue files, and many different files that belong to the actual instantiation of the underlying computing platform. Now, that was just about the stage where we were in about 3 years ago or so. And obviously, not in our area, but in many other areas where this technology started evolving, more and more the issue of semantics came up, because clearly the abstract syntax metamodels, although they represent the so-called structural semantics, it defines the set of all of the possible syntactically correct models. It doesn't tell anything about the behavioral semantics. And the consequences are quite interesting. So, for example, quite nice things that in UML, people can define so-called UML profiles. It's a different mechanism. It's not defining a new domain-specific modeling language. It's, they use another mechanism. And there is a UML profile for timing, schedulability, and performance. Which is using or referring to very rich time models and concurrency models. That's the essence of it. But the semantics is never defined. So clearly, that's just one example. Clearly what happens here is that people with the metamodeling, they can describe the concepts and relationships, well-formed rules, but when you really want to form a sublanguage, which is for deep security-sensitive analysis, if you don't go directly into defining the appropriate semantics for it, the whole thing will become quite shaky. So if I look the state of affairs, what's really accepted these days that the specifications of these domain-specific languages are done, and abstract syntax metamodeling is known and practiced. Many times they call the well-formedness rules as static semantics for it, and that's the point where things usually stop. The behavioral semantic specification, if it is done at all, usually involves a major effort. For example, the state chart semantic specification is still going on in the last 10, 15 years, simply because these languages occasionally are so rich semantically that it's awfully hard to do justice for defining a precise semantics and do a general agreement for it. These efforts use a very wide range of underlying formalisms, and simply because this is expensive and very involved, usually people go into trouble only in few exceptional cases, which is really totally against of the wide use of domain-specific languages in the industry. Now, the impact of this is that what emerges, that the tool chains are becoming closed, and that's again problem, because domain specificity would mean that we can compose tool chains easily, and built around loosely defined conventions in a professional group, and many times a proprietary interpretation of semantics instead of standards. So for example, when in Simulating State Flow, the first hybrid system specifications came out, the semantics of that was the simulation semantics, what Simulating State Flow provide. But what is it? It's in the releases. It's not an explicitly defined semantics. So in a DARPA program where I was the program manager, we spent 2 years to peel off how can we form an agreement for hybrid system semantics specification, which is much more explicit, and define a well understood interchange language with a specified semantics that can be used by many other tools. And obviously the consequence of that many times semantic mismatches can lead to total misunderstanding of how analysis tools provide the results. One tool can tell that the hybrid controller is safe, and the other tool tells it's not safe, depending on what kind of interpretation people had for the underlying semantics. So altogether, the understanding, it's not just mine, but I guess many of us, that model-based design is really, I think it's a wave which cannot be stopped, but it's slowed down quite a bit because the semantics issue is not solved yet properly. Now, let me go to briefly what are we doing on this area, and what is the specification style what we started on. What we follow here is the well-known transformational specification of semantics. Transformational specification of the semantics would mean the following. We have a DSML which doesn't have the semantic mapping from the abstract syntax to the semantic domain. We assume that there is a well-defined DSML, another modeling language, which already has that. It has a well-defined semantics. So the transformational specification of semantics for this DSML would mean that you define the transformation rules, how you translate the models from this DSML into the models to a language which has a well-defined semantic. This is a very common method which is used in the specification of semantics. Now, of course, if we want to pursue this path, we need to make some arrangements. First, we need to standardize the metamodeling language what we use across here. Well, there is an industry standardization effort. For example, MOF is one of the well-accepted metamodeling standards. There are others. Standards really like to multiply. But there is a clear possibility to show equivalence of different kind of metamodeling languages, so that's not a major roadblock. We also need to have a transformation language, a model transformation language. We use basically our model transformation language simply because it's rich enough, and I think it's quite well used these days. But certainly there will be a push to come up with a standard for model transformations, and that's not been closed yet, what will be the output. But of course the question is where are these things are coming from? Because if you want to do the specification of semantic transformation from any DSML, then you have to have things to which you link the specification. Actually that linking what we call semantic anchoring. Fortunately, there is an interesting insight which evolved during the last 10 years or so in system science and in composition. And this is the separation of concern when you do composition. Separation of concern means that when you build systems and do component-based design, these layers are good non-orthogonal but almost orthogonal abstractions, what you can use to describe the overall composed system behavior. You need to have specifications for the component behaviors. These component behavior abstractions that represent behavioral categories, fundamental behavioral categories, are dominantly transition systems like state machines, time automata, continuous dynamics, hybrid dynamics, and others. There is no infinite number of basic behavioral categories what we need. There is a well-defined set of abstraction behavioral categories what we can use for capturing and modeling component behaviors. The second element is that obviously you want to define the structure of the system. So you have components and you represent the behavior with some basic behavioral abstraction. Then you define the structure across the components. But you also need to define what is the interaction, how the elementary components interact with each other. Now it turned out that it's also worthwhile to restrict these possible interaction categories. These restrictions, actually, the name for this, at least in our community, is models of computations. Models of computations like synchronous reactivity, SDF, synchronous data flow, discrete event interactions, define clearly a finite number of methods how a component can interact with each other. There were enough analysis in this that showed that if you don't restrict the interaction times, then you get these totally unanalyzable overall system architectures that are meaningless because you cannot do any decent analysis how they will behave. So there is enough justification that just for the good system design hygiene, you restrict the set of allowable interaction patterns to some what you really understand. Additionally, in modern system design, new issues are coming, such as dynamic structures. It's becoming extremely important to find those those models of computations that guarantee certain fundamental system properties, for example, deadlock freeness or finite buffer lengths. And there are interaction models that provide that. And finally, if you take basic component behaviors, form a structure with selected interaction patterns, even that can be heterogeneous, you come up with an overall composed system which exhibits a set of possible behaviors that then can be linked to resources, and available resources then that finally linearize all of the set of possible behaviors and produce a final behavior set. So basically what we are after is to take that insight and define these sets of semantic units that are basic semantics, behavioral semantics for basic behavioral categories like FSM, hybrid automata, time automata, and others, and interactions, and use these for anchoring different DSMLs to them. Which means that the first element of the overall agenda is to identify these, and the second to codify these on a formal framework. The identification is pretty much worked out during the last decades that what are these basic categories. So what's left now is to go on and select the formal framework and proceed with defining the semantics for it and do the semantic anchoring. We looked around for different formal frameworks. We wanted to have an operational semantics specification style, a formal framework with solid mathematical foundations. We wanted to look properties such as readability, tool support for the validation and exploration of semantics. If you define the domain-specific modeling language and you anchor its semantics, you really want to experiment with it. That's what I wanted. So that's why the tools are so important in this. We want to understand how to do verification of semantic equivalence. So all of these things are combined together, and after evaluating several frameworks, we ended up selecting ASM and the ASML tool suite. And that's how a few of my graduate students started up working on this, and that's the direction what we take. So what are we doing right now? Here is an example for defining the semantics for a synchronous data flow. It's an interaction semantics. All of these specifications have two parts, and this is ASML code actually. All of these specifications have two parts. One is an abstract data model specification. It basically defines the data structure. It is the ASML representation of the abstract syntax. This includes all of the concepts and relationships, but not the well-formatedness rules, because ASML doesn't provide that you define the well-formatedness rules, I guess, for the models. But these are the data structures which we can describe an SDF, a synchronous data flow model. So a synchronous data flow model is modeled as a set of nodes among which there is a set of channels, input ports and output ports, and there is a definition of the ports, there is the definition of the channels, and all of these elements. Okay. Obviously, if you define that abstract data model, you can instantiate it into a concrete data model. And that instantiation will finally represent a concrete data flow SDF structure specification. Now, the other part of it is a model interpreter. That model interpreter describes the semantics, that interaction semantics, in terms of this abstract data model. It basically describes how can I do a run on this synchronous data flow network where we don't model in this the elementary computations that are running in the node. We model it to that level, as it's always the case in interaction semantics, that if a node is becoming schedulable, then it can fire the node. But what is the actual firing, whether you assign to it a particular function or not, is not the objective of that level of semantics. Okay? So basically this model interpreter tells how I can propagate through data on this data flow network. What is the reaction for appearing data elements at the data nodes, and how these propagate through in the network, in the synchronous data flow network. So taking on this whole style, then what we are doing with this semantic anchoring is the following. We form these sets of semantic units for interactions and behavioral categories, and we link it to the domain-specific modeling languages through transformations. Instead of defining every one of the possibly very large number of DSMLs separately as semantics, we turn it upside down, and what we pursue that when you define a DSML, specify the abstract syntax of the DSML, and then think about what kind of semantics you want to assign to it. And that's a very important step to simplify it, to get tractable, analyzable behaviors. Finally, to end up with system specifications, what you can and where you can end up with tool chains where you find analysis tools that can analyze meaningful properties. So the next step is, after you define the metamodel, select the appropriate semantics unit that capture behavioral aspects and specify the semantic anchoring through the transformations. We developed an experimental tool set for doing that. And that tool set has these components. This is our tool environment, which has, of course, this or GME, the generic modeling environment, the transformation specification tools, and we use the ASML tool suite. It was awfully important for us that in the ASML tool suite you have that tremendously nice, elegant interface through which you can write this specification. Then you can take it, compile it down, and you can simulate it, what comes out of it. And indeed, that was a major thing while we selected it and while people started liking it. There is a big modelware project in Europe, and they also picked this up. And I just got their publications that they started using this approach. Actually, the industry engineers like this. So it's also a very important aspect of ASML that it's highly readable. So the GM engineers, the automotive engineers, are not against to read out these specifications in ASML and use the tool suite. So it's really a very important component. Now, so altogether, there's the tool suite. We have the metamodeling and model transformation tools, and we have the former framework and the tools for the specification. So how does it look? It's one example, which is hierarchical finite state machine language we took from Ptolemy, one of my colleagues at Berkeley environment. So it's a hierarchical finite state machine language, and we anchor it semantic to an FSM semantic unit. It's a finite state machine semantic unit. What we need to do. We had the metamodel for the HFSML. We have the metamodel for the finite state machine modeling language, and then we define the transformation rules, how to map the two to each other. Now, obviously, there is a pretty intimate relationship between the metamodel of the FSM semantic unit and the abstract data model. These are basically the same thing, right? This is just a syntactic conversion. We debated how to do that better because we want to automate it as much as possible, that link, that no manual steps are involved. And we have different versions. One version is that we basically capture as metamodels the ASML types, what you provide, and the model transformation do everything. Or we develop the FSM metamodel and we translate from the FSM metamodel into the abstract data models here. So both of these are possible. That's really a detail. So that was the specification on the metamodeling level. Of course, the abstract data model has now the appropriate representation in ASML. The operational semantic specification now for FSMs as rules. And that does basically the semantics specification. When you use it, you gain, for example, the following. We use the HFSM metamodel, generate a modeling environment in which you can build hierarchical state machines. So this is an example for a hierarchical state machine. Then we can generate from these anchoring rules, these transformational rules, an intermediate representation, and that representation is some XML format representation of the model, what you built here. And then we use XSLT to translate it into the data model. And there is no manual thing involved here. The only point that you did manually was build the FSM. And finally, what you end up with is, through that translation process, that you got in the ASML environment a model, an FSM model, what you can simulate and what you can observe. So basically, I can take that model, go through on the translation process, go to the ASML environment, and generate behavioral traces according to the reference semantics. And I can compare this with other things. So if I wrote another transformation and I wrote a code generator for it, I can contrast the traces generated by the code generator with the traces generated by the reference semantics. Now, that's one part of the whole story. So we can create now semantic units and link these transformationally to complex DSML. The next step, of course, is the heterogeneity. And what happens if your DSML has many behavioral aspects? And you have to compose together these complex behavior, and how you do composition in this framework, how you build semantics compositionally. This is the underlying structure, what we experimented with. I will show an example for it. What we follow for the compositional building is the following. Here is an example. Let's take two semantic units. These two semantic units has to be composed together. These semantics units are defined by the abstract data models, by rule sets, and of course the rule sets operate above a state space, which is defined in the abstract state machines. When we want to compose these, there are two sides of the composition. One is a structural composition, which creates links which captured mathematically in form of a mapping between the concept of the abstract data models. That link, I will show an example, that link basically represents things when you take two different kind of behaviors and link together through interactions. And those links, those interactions basically link together concepts. So it restricts the behaviors through this. So that's one part of it, the structural composition. So the obligation here is that you have to define these mappings in terms of the concepts that are in the abstract data model. The second is the behavioral composition, which does the following. We build a higher level controller, basically, on the top of these two semantic units to get this derived semantic unit. And that higher level controller looks for these two semantic units that are representing elementary behaviors, that in the given state, what are the behaviors what you can exhibit now? What is the set of actions what you could execute now? And that's coming up through one of these interfaces, through the get interface, then combines together these enabled set of actions, compose them, and the composition is, I will show an example for it, if there are conflicts, then of course certain actions cannot be composed. Basically what happens here is that both of these elementary behaviors can be modeled as partial orders. The structural composition links these partial orders together, and you basically end up with composing these partial orders to find an overall behavior. And that overall behavior will determine, that controller will basically determine that now what is the set of behaviors what I can implement now by composing these two elementary behaviors. That was a quite interesting example that came up. What Kai Chen, he was my student. He just went to Motorola this month. So he built up this example. Let me just describe what is that model. This is a domain-specific modeling language designed for engine control. The basic components, we called it SCFSL, it doesn't matter. The basic component includes a state machine, and if you look at the transitions on the state machines, they are, of course, the trigger event, the guards, and an output event and actions, possibly many actions. Well, this is a kind of action automata. Events are arriving to the input of one of these components, and the component reacts to it. When the component reacts to it, then it needs to evaluate an action. The action is a function. That function is evaluated over the state space. So they are variables that have to be passed to this function, which gives back a Boolean, whether the guard is true or not. Okay? And the action set has to be evaluated. This action set is also the execution of a set of function, right? When you execute these sets of function, again, they are sitting on the top of a state space, and they pass back parameters to each other or values to each other. So a reaction happens the following way. An event arrives to the event port of a component. This is a data port where data are propagated. The component is right now in a certain state. Wherever the component is, after receiving the event, given this state, the components needs to look what are the guards that has to be evaluated, right? All of those guards that are relevant are evaluated. The result of the evaluation will determine what are the enabled transitions. The transition which is enabled then defines what is the output event which is sent on and generated, and what are the actions that has to be evaluated. So all of those actions has to be evaluated. And then that propagates through. So where is the semantic problem here? What makes it complicated? If you describe it intuitively, it's not obvious that where are the deadlock dangers. Well, the deadlock danger is that all of these actions can pass data to each other. So it's possible that you invoke or you want to execute the action such that data has not been produced to its input. Well, it turns out, after we basically built up compositional semantics, this is really nothing else than a synchronous reactive system modeling language. And that problem, that deadlock problem, is leading to the classical causality problem of these languages, and it has to be analyzed. That was the result of that of this whole semantic anchoring process. So we went through the process. Actually, the whole specification is out on the website. There are the metamodels for it. Then the first step, what Kai did, was take apart and define the component semantics. In this component semantics, obviously, he used the FSM as one semantic unit, and he used the SDF, the synchronous data flow, as another semantic unit. The guards and the actions were put into the SDF semantic unit because that was a crucial element. Yeah. And there were a set of maps that link together these abstract data models. Yeah, and finally, this is the compositional structure of the overall specification that you see that really what happens here, that there is a set of composed FSM behavior and an event flow which is built up. And there is a whole synchronous data flow structure. And what happens is that these two has to be consistent with each other such that you get a consistent reaction. So that comes out from the overall specification. So what are the next steps? We want to proceed with the specification and experimentation of these different semantic units. So that's an involved work, and we verbalize, of course, the ASML enough, but it would be certainly interesting to have help in this. What are the good semantic units? What are the not so good semantic units? These are all issues that are discussed in our community. We certainly are very much interested to go on and work on the theory for that compositional semantic specification, particularly link it to the composition of partial orders and develop some kind of mathematical foundation for it. Automate as much as possible the derivation of those controllers that link together this semantic unit. Certainly the whole thing requires standardization. That's the essence of it. We have a group at OMG, the Model Integrated Computing Group, which is looking into these standardization opportunities. We work together quite a bit in a larger international collaboration. There's a modelware project in Europe. That's one of the collaboration partners. And the ARTIST-2 Center of Excellence program for all of the embedded system research groups in Europe. That's the other thing. So I will just go next week to Finland, where we will discuss some of these issues. And finally, the whole goal, of course, ultimately is to progress toward domain-specific modeling language design tool suite, where you design these languages that are well-founded and validated. And that's basically the goal. Regarding, Yuri told me that, so what MSR can do in this? Well, obviously a lot. First of all, we have very good experience with ASML. It was a pretty panicky thing for us when the ASML disappeared from your website. So it would be very important to get support in a form that the whole ASML research is going on, and we have improvements, additional foundation work such as concurrency models, time, engineering regarding modular specifications, extended tool support, better integratable simulators. So the whole ASML infrastructure is an important issue here. Obviously, it would be good to collaborate with your research group in this. You could give us a whole lot of help to write better specification, better style specification. And of course, the whole standardization effort, which is more of an industry than an academic issue. Okay, that's it.
Thank you very much. You take on such a daunting task.
I think you mentioned in one of the slides there's another layer down there, performance and resource allocation layer. Could you elaborate on that?
Yeah. So if I look at in that compositional semantics framework, in that abstract things, so when you compose these two behaviors, you end up with another behavior which exhibits, again, after the composition of set of possible actions that it can take. Now, at some point at the end of this, you have to decide that at that point, which is the actual behavior what you will take. And that can be decided such that you assign another layer, which is, let's say, a resource allocation layer, which tells that I pick that action now based on priorities. So that decision that after at the end of the composition, I still have freedoms of which actions I select, that selection step is representing the scheduling step, and you can assign to this different kind of optimization criteria on how you want to take that step. That's it.
You mentioned a couple of times using partial orders and then combining them to represent composition systems. Could you say a little more detail on what are the elements in partial order? What's the order relation?
Actions, what the components can take. So, for example, in this GM example, the event propagation chain defines. You see, the whole event flow generates possibly several events that trigger components. These components are ready to execute. When they are ready to execute, every one of these ready to execute component is sitting in a state. In these states, they define a set of guards that needs to be evaluated. So this is a set of actions that should be taken from the point of view of the whole event flow. But all of these guards are linked into a data flow network. This is another semantic unit. And only a part of them might be ready to execute, in fact, because they don't have the data to execute. So the data flow defines one partial order. The event flow defines another partial order. And when you merge these behaviors on that controller level, then basically you merge these two partial orders.
As far as I understand this, you really only merge the events of these two descriptions, but not the states which are used.
That's right.
Yeah.
That's correct. That's correct. So it's not, when I'm talking about the composition, I'm not talking about that sense that you take two automata and then you define the...
I mean, this might be a very valid approach if you're looking really at different components, but if you look at different behavioral aspects of one component, might it not be perhaps handy that we can actually also consider the state when we look at the composition of these aspects.
They are much more open problem here than I can claim.
We'll be over time. Thank you again.
All right, thank you.